The next part in the linear differential equations are those differential equations where instead of having a constant coefficient for the terms like d2y by dx square, d cube y by dx cube, we might be having some multipliers to each of these which are functions of x. Of course, they cannot be any multipliers. It is generally the polynomial which is multiplying the particular coefficient, differential coefficient, like dy by dx will be having some multiplier which is of single degree. d2y by dx square might be having a multiplier which is of second degree, and so on. Now such a differential equation is called as homogeneous differential equation, provided that when we write the differential equation in capital D form, then at every term power of x matches to that of power of y. Just have a look at the given set of problems. Observe the second problem where we have x cube d cube, x square d square, and x raised to 0 d raised to 0. This is homogeneous equation, homogeneous differential equation. Even this can be written as x cube capital D cube plus 3x square capital D square plus x into capital D, and so on. So these are the examples of what are known as the homogeneous differential equations. So these are homogeneous differential equations. Can be very easily identified. Our aim over here will be to convert the given homogeneous differential equation to the standard linear differential equation having the constant coefficients. So we want to get rid of this particular multiplier, and for that we are required to make some substitutions. Let us see how to solve the first problem. I am just writing the problem using capital D operator, that is x square d square minus 2xd minus 4 operating on y is equal to x square plus 2 log x. It will be always the case that the substitution will be log x is equal to z, that is x is equal to e raised to z. So with this substitution we will proceed and try to rewrite the given differential equation. As we have log x is equal to z, we can write dy by dx as dy by dz into dz by dx. Of course, log x equal to z will imply that dz by dx will be simply 1 upon x, and therefore this can be written as dy by dx is nothing but dy by dz into 1 upon x, or when I take x on the left hand side, it is x dy by dx will be written as dy by dz. Let us proceed further to find out d2y by dx square. d2y by dx square can be written as d by dx of dy by dx, which I can rewrite using the chain rule as d by dz of, I am substituting dy by dx as dy by dx is to be substituted okay, let us keep this d by dx as it is. So d by dx into dy by dx is substituted as 1 upon x dy by dz. Now if we differentiate it using chain rule, it will be 1 upon x into d by dx of dy by dz minus 1 upon x square into dy by dz. Now this d by dx can be again substituted by using chain rule as d by dz of some entity, this entity, into dz by dx. So this is dy by dz over here, minus 1 upon x square dy by dz. Now this particular term is nothing but d2y by dz square, and dz by dx we know that it is 1 upon x. So ultimately it will come out to be 1 upon x square into d2y by dz square minus 1 upon x square into dy by dz. And if we multiply throughout by x square, we will get x square d2y by dx square is equal to d2y by dz square minus dy by dz. So we are getting the substitutions for x dy by dx, x square d2y by dx square, and so on. Now temporarily we will declare a new operator, like we have got operator d representing d by dx. Then let us use something like d bar to represent d by dz. Hence x dy by dx, which is coming out to be dy by dz, can be written using operator form as x capital dy will be equal to d bar y, or in short we can say xd is equal to d bar. I am just finding out the corresponding operators. I also have x square d2y by dx square as d2y by dz square minus dy by dz, which can be written as x square d square y equal to d bar square y minus d bar y. That is x square d square equal to d bar square minus d bar, or x square d square is equal to d bar into bracket d bar minus 1. Of course this is a standard substitution, but whatever I have written up till now, that should be associated with each and every problem that we are going to solve. It will be always log x equal to z will be the substitution in case of homogeneous differential equations, that is x is equal to e raised to z. And then we will find dy by dx, which is dy by dz into dz by dx, dz by dx being 1 upon x. We will substitute that and we will get x dy by dx as dy by dz. For d2y by dx square, we will write it as d by dx of dy by dx. Then it will be d by dx of 1 upon x dy by dz. We will use product rule, so it is 1 upon u into v dash. So 1 upon x as it is into d by dx of dy by dz minus, that is plus, actually differentiation of 1 upon x comes out to be minus 1 upon x square, and dy by dz as it is. So it is u v dash plus u dash v. And then this d by dx can be written using chain rule as d by dz into dz by dx, and dz by dx is substituted as 1 upon x, and so both the terms will contain 1 upon x square. We will multiply throughout by x square and get it as x square d2y by dx square equal to d2y by dz square minus dy by dz. Of course the corresponding substitutions we have got, and then we will proceed with rewriting the given differential equation, this time in terms of y and z. So I will have to write x square d square as d bar into d bar minus 1 minus 2 d bar minus 4 operating on y equal to x square. Now x was e raised to z, so this will be e raised to 2z plus 2z, log x is z. Now from henceforth, instead of writing d bar every time, I will use d square only, but remember that d is nothing but d by dz in this case. So it will be d square minus d minus 2d minus 4 bracket complete operating on y equal to e raised to 2z plus 2z. Once we convert it to the standard linear differential equation form, then the job is pretty simple. You will have to find out CF and PI, but at the end we are required to resubstitute z as log x. So ultimately it comes out to be d square minus 3d minus 4 operating on y equal to e raised to 2z plus 2z. For CF, auxiliary equation is d square minus 3d minus 4 operating on y equal to 0. Therefore d square minus 3d minus 4 equal to 0. which is nothing but d minus 4 into d plus 1 equal to 0, that is d equal to 4 or minus 1. CF in this case will be C1 e raised to 4, not x, because it is d by dz, which is capital D. So it will be C1 e raised to 4z plus C2 e raised to minus z. CF. For Pi, it will be 1 upon d square minus 3d minus 4 operating on e raised to 2z plus twice 1 upon d square minus 3d minus 4 operating on z. Here substitution by formula number 1, short method, 1 upon f of d operating on e raised to ax is 1 upon fa into e raised to ax. We are required to replace a d by a in this case is 2. So it will be 1 upon 2 square minus 6 minus 4 e raised to 2z. Whereas here I will have to take constant outside and write it as 1 plus or 1 minus form. So it will be 1 minus d square minus 3d upon 4 operating on z. This is by using formula 5. So here I have used formula 5 and here I have used formula number 1. So this ultimately comes out to be 4 cancels. It is e raised to 2z upon minus 6 minus half. This will be 1 minus d square minus 3d upon 4, bracket complete, bracket raised to minus 1 operating on z. Now 1 minus t bracket raised to minus 1 is nothing but 1 plus t square, etc. We are required to expand it to the maximum power of z, which is in this case 1. So we want to go only up to the first power. So this can be written further as e raised to 2z upon minus 6 minus half. It is 1 plus t, so 1 plus d square minus 3d upon 4 operating on z. Now d of z is 1, d square of z is 0. So this will be e raised to 2z upon minus 6 minus half into bracket. When 1 operates on z, it is z, plus d square operating on z is 0, minus 3 by 4 d operating on z is 1. Ultimately answer comes out to be e raised to 2z upon minus 6 minus z by 2 minus minus plus 3 by 8, which is Pi. And y equal to Cf plus Pi will be the required answer. So y will be equal to C1, it was e raised to, what was Cf? E raised to 4z plus C2 e raised to minus z plus e raised to 2z upon minus 6 minus z by 2 plus 3 upon 8. And when we resubstitute for z as log x or e raised to z as x, this will turn out to be C1 x raised to 4 plus C2 upon x plus rather minus x square by 6 minus half log x plus 3 by 8 will be the required solution of the given homogeneous differential equation. So there is a substitution by which we will be converting the homogeneous differential equation to the linear differential equation with constant coefficients, and then solving it by using our standard way of CF and Pi, and then resubstitute z as log x or e raised to z as x. Substitution in all cases is going to be log x is equal to z. Let us solve the second problem. Actually, I did not solve all the problems till the end because it is CF and Pi that we are very well familiar with. So it is x cube d cube plus x square d square minus 2 operating on y is equal to x plus 1 upon x cube. Substitution is let log x is equal to z. Therefore, x is equal to e raised to z, and dz by dx is equal to 1 upon x. You will have to write this every time, that is dy by dx is nothing but dy by dz into dz by dx, which is equal to dy by dz into 1 upon x, and therefore x dy by dx is equal to dy by dz, which implies that xd is equal to d bar. To find d2y by dx square, it will be d by dx of dy by dx, which will be written as d by dx of 1 upon x dy by dz, can be expanded by the product rule of differentiation. It will be 1 upon x d by dx of dy by dz minus 1 upon x square dy by dz. Using chain rule over here, it will be 1 upon x d by dz of dy by dz into dz by dx minus 1 upon x square dy by dz. So this will turn out to be, this dz by dx is 1 upon x, so it is again 1 upon x square d2y by dz square minus 1 upon x square dy by dz. If we multiply throughout by x square, we get it as x square d2y by dx square equal to d2y by dz square minus dy by dz, which ultimately tells us that it is x square d square written as d bar square minus d bar, that is d bar into bracket d bar minus 1. It will not be sufficient in this case to go only up to x square d square, because we are required to even find out x cube d cube, and for finding x cube d cube we will have to continue with the same procedure. Here we are finding dy by dx, here we are finding d2y by dx square, and now to find d cube y by dx cube we will use the same technique, that is it is d by dx of d2y by dx square, which we can very easily substitute. This will be substituted as d by dx of 1 upon x square d2y by dz square minus 1 upon x square d2y by dz. Procedure is exactly the same, no change in the procedure. You will have to determine it in the same manner. And so when you differentiate this by the product rule, it will be 1 upon x square d by dx of, instead of that I will write it as d by dz of d2y by dz square into dz by dx. Then differentiation of 1 upon x square will be minus 2 upon x cube d2y by dz square. The third term will be written as minus 1 upon x square into d by dz of d2y by dz. Hello, this should be dy by dz. It will be d by dz of dy by dz into dz by dx, and then differentiation of 1 upon x square will be minus minus plus, this time 2 upon x cube dy by dz. As we substitute dz by dx as 1 upon x, we can take 1 upon x cube common throughout, and the terms which will remain are, from the first one it is d cube y by dz cube, from the second one it is minus 2 d2y by dz square, from the third one it is minus d2y by dz square, and from the last one it is plus 2 dy by dz. So ultimately this will be 1 upon x cube into bracket d cube y by dz cube minus 3 d2y by dz square plus 2 dy by dz. And in the capital D form, when you take it on the left hand side, it will be x cube d cube y by dx cube will be equal to d cube y by dz cube minus 3 d2y by dz square plus 2 dy by dz. That is, x cube d cube will be equal to d bar cube minus 3 d bar square plus 2 d bar, and if you take d bar common and write it in the standard form, it will be d bar into d bar minus 1 into d bar minus 2. So we have found the third coefficient, x cube d cube. And now, using these values of x cube d cube, x square d square, xd, we will proceed to the given differential equation and make the substitution. All this has to be written along with every problem. You will have to go to that particular position which has been used in the given differential equation. It could be x square d square, it could be x cube d cube, and so on. So as we substitute here in the given differential equation, it will be d bar into d bar minus 1 into d bar minus 2, x cube d cube is substituted, plus d bar into d bar minus 1 minus 2, bracket complete, operating on y. Now x is nothing but e raised to z, so it will be e raised to z plus e raised to minus 3z. Simplicity, I will write it as d bar ke bajaye d, and so this will turn out to be d cube minus 3d square plus 2d plus d square minus d minus 2, bracket complete, operating on y equal to e raised to z plus e raised to minus 3z. And so this will be d cube minus 2d square plus d minus 2, operating on y equal to e raised to z plus e raised to minus 3z. For CF, it will be d cube minus 2d square plus d minus 2, bracket complete, operating on y equal to 0, is nothing but the auxiliary equation. So it will be d cube minus 2d square plus d minus 2 equal to 0. We can take d square common from first two, it will be d square into bracket d minus 2 plus 1 into bracket d minus 2 equal to 0. Factors will be d square plus 1 into d minus 2 equal to 0. And so we get it as d square equal to minus 1 or d equal to 2, that is d equal to plus or minus I, complex roots, and d equal to 2, the only real root that we have. There are three roots, there will be three constants in the complementary function, namely C1, C2, C3. Apply the rule for the real and distinct formula for the real root, and for complex distinct you will be using the third formula, e raised to alpha x into bracket C1 cos beta x plus C2 sin beta x. And so CF in this case will turn out to be C1 e raised to 2x, that is for real root, plus e raised to 0x, real part in this case is 0, into bracket C2 cos x plus C3 sin x, beta is 1. Ultimately CF comes out to be C1 e raised to 2x plus C2 cos x plus C3 sin x. Once we find CF, we will have to proceed to find out Pi, and for Pi it is 1 upon Fd operating on capital X. So Pi will be equal to 1 upon, even if we write it in the factors form, d square plus 1 operating on d minus 1 is operating on e raised to z plus 1 upon d square plus 1, it was d minus 2, d square plus 1 into d minus 2 operating on e raised to minus 3z. Job is pretty simple. Using formula 1 we are required to replace d by a. A in this case is 1. If we substitute it at every place, nothing is becoming 0. Formula 1 can be applied safely. Whereas here we are required to replace d by a is minus 3, and again it is not becoming 0. In a single step we will be getting the answer. It will be 1 upon 1 plus 1 into 1 minus 2 into e raised to z plus 1 upon minus 3 square is 9 plus 1 into minus 3 minus 2 e raised to minus 3z. So this is 2 minus 1, so it is minus half e raised to z, and this will be 10 into 5 minus 1 by 50 e raised to minus 3z. Y equal to Cf plus Pi is the required answer. So this time it will be y equal to, it was C1 e raised to 2x plus C2 cos x plus C3 sin x minus e raised to z upon 2 minus e raised to minus 3z upon 50. And as we substitute x equal to log x or e raised to x is equal to z, as we substitute x equal log x is equal to z or e raised to x is equal to z, as we substitute, the substitution was log x is equal to z, that is x is equal to e raised to z. We have made a mistake while writing this. This should be in terms of z. Even for the first time when I have written Cf, that was a mistake, which is a common mistake that most of the students, including teachers, commit at times, because d over here was d by dz and Cf should be written in terms of z and not in terms of x. So Cf in this case comes out to be C1 e raised to 2z plus e raised to 0z into bracket C2 cos z plus C3 sin z, and so it will be C1 e raised to 2z plus C2 cos z plus C3 sin z. And that's why when we substitute log x equal to z or x equal to e raised to z, final answer comes out to be C1 x square plus C2 cos of log x plus C3 sin of log x minus x by 2 minus 1 upon 50 x cube. That will be the required answer. This mistake is very obvious because we are solving almost all the problems where we are using d by dx. We should be rather cautious when the substitution is made and d was converted to d by dz. For simplicity we had converted d bar to d, and then we are always landing up in the trouble when we write Cf. Cf should be in this case in terms of z. Pi will come out to be in terms of z only, and y equal to Cf plus Pi, replace z by log x. That was problem number 3. Problem number 2. Let us proceed to problem number 3. It was x cube d cube plus 3x square d square plus xd minus 1 operating on y equal to 3x minus 7. Substitution is obvious. Xd equal to d bar, x square d square is d bar into d bar minus 1, and x cube d cube is d bar into d bar minus 1 into d bar minus 2, where capital D is d by dx, whereas capital D bar is d by dz. So it will be written as, and of course the substitution was let log x is equal to z, and that's why we are getting all this thing. So as we substitute, it will be d bar into d bar minus 1 into d bar minus 2 plus 3 d bar into d bar minus 1 plus d bar minus 1. This whole thing operating on y is equal to 3 e raised to z minus 7. Again, for the simplicity, we will be replacing d square by d and remembering it as d by dz. This will turn out to be d cube minus 3d square plus 2d plus 3d square minus 3d plus d minus 1 operating on y equal to 3 e raised to z minus 1 minus 7. 3d square cancels, 2d minus 3d and plus d cancels. Ultimately it comes out to be d cube minus 1 operating on y equal to 3e raised to z minus 7. For CF, d cube minus 1 operating on y equal to 0 is the auxiliary equation, and therefore d cube minus 1 equal to 0. A cube minus b cube is a standard formula, a minus b into another bracket a square plus ab plus b square, and therefore we get d equal to 1 or d equal to, using quadratic formula, minus b plus or minus under root b square minus 4ac divided by 2a, and so we get it as minus half plus or minus I root 3 by 2. CF will come out to be C1 e raised to, now we should be careful, it should be z plus e raised to minus z by 2 into bracket C2 cos of root 3 by 2 z plus C3 sin of root 3 by 2 z is CF. Cubic equation, we should get 3 constants in the complementary function. Now Pi can be written as 1 upon d cube minus 1, 3 can be taken outside operating on e raised to z, minus 7 1 upon d cube minus 1 operating on e raised to 0z. Now if I substitute d equal to 1 over here, it becomes 0. So we will have to factorize the first one. It is 1 upon d minus 1 into d square plus d plus 1 operating on e raised to z. Whereas in the second case, d can be replaced by the constant a, coefficient of z, and it doesn't become 0. So it is 1 upon 0 minus 1 operating on e raised to 0z. Here I have applied formula 1. Now I will be applying formula 1 for the second term, because it is not becoming 0. So it will be 3 1 upon d minus 1 into bracket 1 plus 1 plus 1 operating on e raised to z minus 7 upon minus 1 into 1. So this 3 over here will get cancelled, and this is 1 upon d minus a bracket raised to r operating on e raised to ax with the formula as x raised to r upon r factorial into e raised to ax. R is 1, so this can be written as x raised to r, x in this case is z, so it is z raised to 1 upon 1 factorial into e raised to z is the answer of the first one, and minus minus plus 7. So ultimately answer comes out to be z e raised to z plus 7 is Pi. And then we will write the answer as y equal to CF plus Pi. We will be writing the answer as y equal to CF plus Pi, and then it will be y equal to C1 e raised to z plus e raised to minus z by 2 into bracket C2 cos of root 3 by 2 z plus C3 sin of root 3 by 2 z plus z e raised to z plus 7, and substitution was log x equal to z, that is x equal to e raised to z, and so it will be C1 x plus x raised to minus half into bracket C2 cos of root 3 by 2 log x plus C3 sin of root 3 by 2 log x plus z is log x and e raised to z is x, so plus x log x plus 7. So that is how problem number 3 is solved. On the same lines we will be solving the remaining problems also, problem number 4, 5 and so on. and in all the cases we will be having the same substitution, and the answers will also be also written in terms of x at the end. Don't leave the answer till the point of z. We won't be getting marks for that. So that was problem number 3. Problem number 4. It is a bit complicated or rather time consuming, because we are required to every time show the derivation for xd, x square, d square and so on. Right now we are not writing all of them. First 2 problems I had written it. From third problem I am not writing it, but you will have to write it every time. Fourth problem, it is x square d square minus xd plus 4 operating on y equal to cos of log x plus x sin of log x. Substitution, let log x is equal to z, that is x equal to e raised to z. Therefore, xd equal to d bar, x square d square equal to d bar into d bar minus 1, where capital D is d by dx and capital D bar is d by dz. As we substitute, it will be d bar into d bar minus 1 minus d bar plus 4 bracket complete operating on y equal to cos of log x is nothing but z, so cos z plus x is nothing but e raised to z, so e raised to z sin z. And so this can be written as d square minus d plus 4 bracket complete operating on y as cos z plus e raised to z sin z. D square minus 2d plus 4 operating on y equal to cos z plus e raised to z sin z is to be solved. For CF, auxiliary equation is to be written. So for CF, it will be d square minus 2d plus 4 bracket complete operating on y equal to 0, which is nothing but the auxiliary equation. And to find d, we will use the quadratic formula. You cannot factorize it, it is not a complete square. So d equal to minus b plus or minus under root b square, that is 4 minus 4ac divided by 2a, and so this will turn out to be 2 plus or minus under root of minus 12 upon 2. 4 can be taken common, 2 cancels throughout, it will be 1 plus or minus I root 3. And so CF in this case will come out to be e raised to alpha x, that is alpha z in this case, e raised to z into bracket, it is c1 cos of root 3z plus c2 sin of root 3z. That was CF. For PI, we will separate out the terms. It is 1 upon d square minus 2d plus 4 operating on cos z plus 1 upon d square minus 2d plus 4 operating on e raised to z into sin z. Here we will be using formula number 3, which says that replace d square by minus a square. A in this case is 1, minus a square will be minus 1. It will be 1 upon minus 1 minus 2d plus 4 operating on cos z. We don't have any substitution for d. It is by the use of formula number 3. Whereas in the second case it is a product. E raised to z can be taken outside, and when e raised to z goes outside 1 upon f of d, it will be replacing d by d plus a. A in this case is 1, so it will be replacing d by d plus 1. So So it is d plus 1 bracket square minus 2 into bracket d plus 1 plus 4 operating on sin z. This is with the use of formula number 6. So the first term comes out to be 1 upon 3 minus 2d. This is 1 upon 3 minus 2d. And to get d square in the denominator, you will have to multiply and divide by 3 plus 2d. So this will turn out to be 3 plus 2d divided by 9 minus 4d square operating on cos z plus e raised to z 1 upon expand. It is going to be d square plus 2d plus 1 minus 2d minus 2 plus 4 operating on sin z. And so when we apply formula number 3 again to the first term, it will be 9 minus 4 into minus 1 into cos z plus e raised to z 1 upon, the denominator will be simplified because 2d term gets cancelled and it will be simply d square plus 3 in the denominator operating on sin z. You will have to apply formula number 3 again, and here this will be 9 plus 4, 13, 1 upon 13 goes outside, 3 cos z plus 2 times differentiation of cos z is minus sin z plus e raised to z 1 upon minus 1 plus 3 sin z. This is again with the use of formula number 3. And so final answer comes out to be 1 upon 13 into bracket 3 cos z minus 2 sin z and plus it will be e raised to z sin z upon 2. Y equal to Cf plus Pi is the required solution, which will be e raised to z into bracket C1 cos of root 3z plus C2 sin of root 3z plus 1 by 13 into bracket 3 cos z minus 2 sin z plus e raised to z sin z upon 2. And then we are required to resubstitute z. Our substitution was log x equal to z. And so e raised to z will be, it was log x is equal to z, and therefore x equal to e raised to z. Both ways we are required to substitute. So e raised to z is x. So it is x into bracket C1 cos of root 3 log x plus C2 sin of root 3 log x plus 1 by 13 into bracket 3 cos of log x minus 2 sin of log x plus e raised to z is x into sin of log x upon 2. A bit lengthy answer. That was problem number 4. So the problems of homogeneous differential equations which we were solving up till now, that particular form of homogeneous differential equation is known as the Cauchy's form. This is Cauchy's form. And now what we are going to learn is called as the Legender's form. These are the two types of homogeneous equations which we are required to study. So up till now we were solving the problems of Cauchy's form, and problem number 5 and 6, they will be in the Legender's form. And you can observe that in both these cases we don't have the multiplier which is directly the power of x, but it is some polynomial of x which is coming into picture, and first of all we are required to get rid of that particular term which is 2x plus 1 or x plus 2. And once we get rid of that particular term, then the equation will turn out to be homogeneous in some variables, and then we will be going for our standard substitution like log x equal to z, solving it, and while resubstituting we will be again having two steps. One which will remove that particular log type of substitution, and the other which will get us back to 2x plus 1 or x plus 2. So problem number 5, it was 2x plus 1 bracket square d2y by dx square minus 2 into 2x plus 1 dy by dx minus 12y equal to 6x. The very first substitution will be let 2x plus 1 is equal to u. If 2x plus 1 is u, then obviously du by dx will be 2. Now see that when we want to substitute for dy by dx, it will be written as dy by du into du by dx, and so du by dx is 2, so it will be 2 dy by du. d2y by dx square will be d by dx of dy by dx, which will be written as d by dx of 2 dy by du, and using chain rule it will be d by du of 2 dy by du into du by dx, and du by dx is again 2. Ultimately this 2 will come out and this value is also 2. It will be 4 times d2y by du square. In general we can say that if it is ax plus b equal to u is the homogeneous substitution, then dy by dx can be written as a dy by du, d2y by dx square can be written as a square d2y by du square, d cube y by dx cube can be written as a cube d cube y by dx cube, and so on. So we have already shown the steps for this particular generalization. Again, cannot be written directly in the exam. These steps are to be shown, and so when we substitute, the given differential equation will now turn out to be 2x plus 1 is u, so u square into 4 d2y by du square minus 2u into 2 dy by du minus 12y equal to, the substitution was 2x plus 1 is equal to u, so 2x is equal to u minus 1. Obviously 6x will be 3 into u minus 1, so right hand side will be written as 3 into u minus 1. Let us represent it in the capital D form. Keep remembering that capital D in this case will be d by du. So it will be 4u square d square minus 4ud minus 12 bracket complete operating on y equal to 3 into u minus 1. Capital D is nothing but d by du. Four can be taken common from left hand side, and it will turn out to be u square d square minus ud minus 3 bracket complete operating on y equal to 3 by 4 into bracket u minus 1. Substitution over here like homogeneous. When we had x square d square, substitution was log x equal to z. Here it will be log u equal to z. That is u equal to e raised to z. Obviously you will say that ud equal to d bar, u square d square equal to d bar into d bar minus 1, where d is d by du and d bar is d by dz. Substitute, so it will be d bar into bracket d bar minus 1 minus d bar minus 3 bracket complete operating on y equal to 3 by 4 into bracket e raised to z minus 1. Simplicity, we will be writing d bar as d. It will be d square minus d minus d, d square minus d minus d minus 3 operating on y equal to 3 by 4 e raised to z minus 1. So the equation that we want to solve, which is in the linear differential equation form with constant coefficients, is d square minus 2d minus 3 bracket complete operating on y equal to 3 by 4 into bracket e raised to z minus 1. For CF, it will be d square minus 2d minus 3 bracket complete operating on y equal to 0, that is d square minus 2d minus 3 equal to 0, which is nothing but d minus 3 into bracket d plus 1 equal to 0, and so d will be equal to 3 or minus 1. So CF comes out to be C1 e raised to 3z plus C2 e raised to minus z. For PI, we have a formula 1 upon d square minus 2d minus 3 operating on 3 by 4 e raised to z minus 1. Separate it out, it will be 3 by 4 1 upon d square minus 3d d square minus 2d minus 3 operating on e raised to z minus 3 by 4 1 upon d square minus 2d minus 3 operating on e raised to 0 z. 1 is written as e raised to 0 z. Formula says that replace d by a. A in this case is 1, so it can be written as 3 by 4 1 upon 1 minus 2 minus 3 e raised to z minus 3 by 4 1 upon 0 minus 0 minus 3 e raised to 0 z. 1 minus 5 is minus 4, so this will be minus 3 e raised to z by 16, and in the second case minus 3 cancels and you will have it as 1 by 4. Y equal to CF plus PI is the final answer. So y equal to CF plus PI, which will be equal to C1 e raised to 3z plus C2 e raised to minus z minus 3 e raised to z upon 16 plus 1 by 4. But substitution was log u equal to z or u equal to e raised to z, and so it will turn out to be C1 u cube plus C2 upon u minus 3u by 16 plus 1 by 4. But u was 2x plus 1, and so the final answer will be C1 into bracket 2x plus 1 bracket cube plus C2 upon 2x plus 1 minus 3 into 2x plus 1 upon 16 plus 1 by 4 is the required solution for problem number 5, which was the first problem in the Legender's form for the homogeneous differential equations. Now we are left with one more problem in the Legender's form, which is x plus 2 bracket square d2y by dx square minus x plus 2 dy by dx plus y is equal to 3x plus 4, to be solved exactly on the same lines. So problem number 6. It was x plus 2 bracket square d2y by dx square minus x plus 2 dy by dx plus y equal to 3x plus 4. Substitution was let x plus 2 is equal to u, and therefore you will have dy by dx as dy by du, and also d2y by dx square as d2y by du square, because over here coefficient of x is 1. So the substitution is straightforward, a linear one. There is not even a scalar multiplier to the generated differential coefficient in this particular case. And so as we substitute, this will turn out to be u square d2y by du square minus u dy by du plus y is equal to, it will be 3 into u minus 2 plus 4. As we write it in the capital D form, it will be u square d square minus ud plus 1 operating on y equal to, it will be 3u minus 2, this is minus 6 plus 4, where capital D is nothing but d by du. Substitution is let log u equal to z, that is u equal to e raised to z. Therefore, ud will be equal to d bar. U square d square will be d bar into d bar minus 1, where d is d by du and d bar is nothing but d by dz. So this will be d bar into bracket d bar minus 1 minus d bar plus 1 operating on y equal to 3. U is nothing but e raised to z minus 2. So this will be, for simplicity, replacing d bar by d, it will be d square minus d plus 1 bracket complete operating on y equal to 3 e raised to z minus 2. And so the differential equation will be now in the form d square minus 2d plus 1 operating on y equal to 3 e raised to z minus 2. For CF, it will be d square minus 2d plus 1 operating on y equal to 0. That is d square minus 2d plus 1 equal to 0, which is a perfect square. So d equal to 1 comma 1. Roots are real and repeated. We are required to apply formula number 2 for finding CF. And so CF will turn out to be C1 plus C2 not x, z e raised to 1z CF. For PI, PI will be 1 upon d square minus 2d plus 1 operating on, I will write it separately, 3 e raised to z minus twice 1 upon d square minus 2d plus 1 operating on e raised to 0z. Now as I substitute d equal to 1 in the first case using formula number 1, it comes out to be 0, obviously, because d minus 1 was the factor of the fd equal to 0 equation as such. And so let us write it as in the proper form as d minus 1 bracket square operating on e raised to z, which will lead to formula number 2, whereas in the second case d is to be replaced by 0, which can be easily done. So it is 0 minus 0 plus 1 e raised to 0z. This is where I have applied formula number 1 for short methods of PI. And here I am required to apply formula number 2, which says that 1 upon d minus a bracket raised to r operating on e raised to ax is nothing but x raised to r upon r factorial e raised to ax. And so this will be written as 3 into x raised to r, x in this case is z. So z square upon 2 factorial e raised to z minus 2 into 1. So this will be 3z square e raised to z upon 2 minus 2 will be the PI. Y equal to CF plus PI will be the required answer. And so it will be C1 plus C2z into e raised to z plus 3z square e raised to z upon 2 minus 2. But we had a substitution log u equal to z, that is u equal to e raised to z. So we will proceed with that. It will be C1 plus C2 log u into e raised to z is nothing but u plus 3 z square, that is log u bracket square into e raised to z, that is u divided by 2 minus 2. But u is nothing but x plus 2. So substitute. So it is going to be C1 plus C2 log of x plus 2 bracket complete into another bracket x plus 2 plus 3 by 2 log of x plus 2 log the whole square into x plus 2 minus 2 will be the required answer for the second problem in the Legender's form of homogeneous differential equations. So this is one more type which is very easy to identify. For the first time we will be having some multiplier, some variable multiplier for dy by dx or d2y by dx square, etc. If we cannot eliminate it, then try to bring the equation in the homogeneous form. That homogeneity is maintained with each term, and homogeneous differential equation is the one where every term will have same power of x and d into it. If it is not there, then try to adjust it. If we can't adjust it, then it is not the homogeneous differential equation.